All right, so put everything back in your bag.
Make this because of the American apocalypse.
No. Do that one for you real quick. All right. Here, Annabelle, take that one back. Okay, I'm gonna go over them real quick for you.
Miss Sanders, you got one.
You got one more? You got one more. All right, that's it.
I have one more too.
And you got one more too. Yes. All right, so
What did they do in that?
I'm gonna real quick go over these for you. So everybody come in where you can hear. Let's say them all together. What is number one?
Your mother was a Spider-Man.
Very good. Number two.
Dresses you funny.
Very good. Number three.
You have dog.
Can I answer number 13?
We have dog breath, right?
Yeah, number 13. Yeah.
Number four. Good. Number five. Good. Number six. Biology is the best subject. Number seven. Drink water every day. Number 8 is, again, Lucas, I love music. Number 9, we are all adorable puppies. Number 10, biology is so much fun. Number 11, education
Is
door to the future. Number 12, your father wears a suit. 13,
My brother wears nothing.
your brother wears nothing. Number 14,
I thought we're gonna say it.
14,
we are all in this together.
15,
15, we must be informed every day.
very good. 16, rock and roll music
It's my
is the best. 17,
Biology is all around you.
very good. 18,
Yeah.
read a little
Every day.
every day. 19,
These are the code for life.
good. 20,
Yeah,
okay, who got all 20?
No,
How about 19, 18, 17, 16, 15? Some of you got some of them. All right, good. That was good.
Yeah.
That's tricky, right? Okay, juniors, you're dismissed. And I'm gonna give you seniors like listen. Lab rat, juniors, you're dismissed. Lab rats, take like 2 minutes to pack everything back up neatly the way you found it and put it back on the counter the way you found it. You can hang on to or throw away those other slips, I don't care. Good job. Yeah, it's a little puzzle cube. I don't.
We have dog breath.
You have dog breath. Yep, that was one of them. We have dog breath. I didn't make it up. It is what it is.
It's all true.
I bought that lab. I did not make that lab. I bought that lab. Yeah, bought that lab on Teachers Pay Teachers, which is excellent.
Sammy,
Yes,
Oh,
I
this
can't believe you're gonna let me know if you-
just step out if you need to.
is on right.
Lots of people are on there. It's a really good.
Mr. DeMail is a really funny educational YouTuber.
Yeah, I know. He's good. I've got a Teachers Pay Teachers shop too. And the big forensic genetic genealogy lab I'm working on, I'm putting out there. There's nothing else like it out there, so I'm hoping people will actually buy it, but it's going to have to be expensive because it's taken me over a year now to make it and it's not done.
I'm trying to sign up for next semester's spouses and they don't have an English too.
Oh,
But I'm doing criminal justice and
very good.
feel free.
Yeah.
Do you
Great.
so Jay, but YouTube, so I'm coming in.
That sounds like fun.
Yeah. Funny thing is, one of my classmates is going into criminal justice, so I might see her in that class. But I've chosen the teachers that have the best ratings.
Good. That's smart. Always look at rate my professor.
I don't have a choice for my major because it's the same two teachers.
So rate my professor is interesting, right?
So good.
It's like, there's a rate my teacher too, but rate my professor is really interesting because it gives you like opinions on professors.
Yeah.
And here's why I find it so daggone funny. So my mother-in-law has been a college English professor her entire professional life. My father-in-law, when he retired from being, first he was a fighter pilot, then when he left the Navy, he became an airline pilot. And when he retired They force you to retire at 65 if you're an airline pilot. It's a forced retirement at that age.
makes sense.
Yep.
And oh, you went.
Absolutely. So he was hanging around the house making her crazy. So she insisted he put his MBA to use and go teach business classes at college. So he was at the community college teaching business classes. And if you look up his Rate My Professors, there was a school year, I don't even remember what year it was, where somebody wrote that he was so hot. And then like 5 or 6 other students came back and wrote about how hot he was, which is hilarious. It was Tidewater Community College. It was just a thing. Like people got into it. Oh, and Mr. Stark is just the hottest. It was so, when you read through it, it's so funny because like, I mean, I'm not saying he's not like a nice looking man, he is, but it's just funny. Like he's not the kind of guy that he's not like George Clooney, like older guy, like smoldering kind of a thing. So it's hilarious that there's this whole string of comments about how hot he is. Makes me laugh every time I read it. I'm like, this is genius. Who did this? And I think he saw it and went, oh, yeah, whatever. That's kind of his reaction to everything. All right, so we've got today, we've got next week, and that lab is going to be isolating your own DNA so you can visualize it, which is really fun. And then after that, we've got reviews and finals and presentations, and you are sprung. Yay, it'll be summer. Hey, James is like, I'm done, right? The man is done. PJ, for criminal justice things, something to consider. When's your 18th birthday?
Not this year, but next year.
Next year, right? Yeah, okay. So Cole just started doing something that he's super excited about. He is a victim services advocate with the Waco Police Department now. So he just finished academy last week and his first shift will be next Friday. So he gets to go on like calls for domestics, things like that, death notifications. He's the guy that's the liaison between the department and the victim to be like, these are your resources. These are your rights, all of that. He gets to transport people to safe houses and gets a car with lights and a radio. So he's very excited about the light bar and the radio in the car. Yeah. So
I understand forensic pathology, which means I have to get chemistry, biology, and all pre-med.
And I was going to say another option for you to consider is look for Boy Scouts Explorers programs for their pre-med. Because I did that in high school and I got to go to the gross anatomy lab at the local med school. So we were all up in the cadavers. You would probably prefer like Boy Scouts Explorers. Yeah, it's open to all genders, Boy Scouts Explorers. So it's not strictly boys only, and it's really cool. They have a law enforcement one too, I think, though. I'm not sure, but yeah. It was really cool. Like gross anatomy lab was awesome. All right, so we are going to do lesson 31, which is our second lesson for organic or biological chemistry. Pay attention to your final exam review materials. Not every little tiny detail is going to be on there from these last couple quick lessons with nuclear and organic chemistry. So if you go through your reviews, you'll have an idea of what you actually are going to be responsible for. I don't throw surprises at you. There are problems. There are going to be some problems you have to work, and you should know what they are based on your review packet. So know what kinds of problems they are. They might even be the exact same problems. You never know. So there shouldn't be any surprises on that final. That's right, James. You are right. So we're going to start by talking about carbohydrates and lipids. So does anybody want to define a carbohydrate for me, James? Carbon and what else? And hydrogen. Yeah. So really what you have are naturally occurring compounds or a derivative of that compound with a general chemical formula that is some number of carbons with an oxygen and sometimes what you'll call a functional group, which would be the little Y thing plugged onto the end there. And they make up, they're made up of molecules of carbon, hydrogen, and oxygen. Hydrogen and oxygen typically in the state of water combined as water. So the most widespread organic substances are carbohydrates. If you glance out the window, most of the stuff you see out there that's not, like the metal deck rail or any of that kind of business, it's all carbohydrates, all of it. Now we hear people when they're dieting talk about I'm cutting carbs, right? So what they're cutting typically are what? What do people that are cutting carbs not eat?
Carb-dense foods.
Yeah, carb-dense foods like what? Somebody back there said it. Bread, not meat. Meat's protein typically, but we think of it that way when we eat. Yeah, with breads, rice, grain, pasta, all those carbohydrates that very quickly break down in the body into sugars. Because what happens to sugar that you don't convert into energy?
It turns into fat.
It turns into fat. So yeah, so people who are like, oh, I'm cutting carbs, like, there you go. There's, it was interesting about, probably now about 20 years ago, there was a cardiologist who created a diet that was supposed to be a heart healthy diet. It was geared towards trying to help some of his heart patients become healthier and have less issues and whatever. And that actually turned into the South Beach diet, which was like a huge craze for cutting carbs for weight loss. It wasn't intended for weight loss, but boy, did people lose weight. And basically it's a 3-phase diet, and your first phase is like no carbs, no major carbs. Obviously there's carbs in like a steak, but you could eat steak and cheese and veggies and stuff all day, but like no potato, no rice and that kind of thing. And you went through phases, but it was very effective for weight loss, and it was very effective for getting all of your like blood levels and stuff in check, right? We used to do the pyramid when your parents and I were in school. It was this little food pyramid, and at the bottom of it was all the carbs, and you're supposed to eat like 8 servings a day or something like that. Yeah, now it's a plate. It's a little different because people were pigging out on carbs, and now we have like this grossly overweight nation of people, right? So we told everybody, eat all the rice, a bunch all day long, and eat all the pasta, and then we all got fat, and they're like, why are we fat? Okay, I wonder why. So carbohydrates play a vital role in all life, completely necessary, and in pretty much every living thing here. So carbohydrate structures, these are hydrates of carbon. So they have kind of a generic structure of your carbon and then a water. Okay, we'll pull back car, let it go one time so it stops making noise, and then quit with it. I know they're noisy little things. So we have 3 main types of carbohydrates: monosaccharides, disaccharides, and polysaccharides. So let's break that down a minute. Monosaccharides. Mono means? One. Good. Everybody got that one. What does saccharide mean?
Sugar.
Close. Sweet. Which basically means 1 sugar, right? Sweet. 1 and sweet. Most common of these sugars, they're simple sugars. The most common of them would be glucose. Where do you find glucose, James? Do what? The cell cycle? Yeah. Cellular respiration is, it's a product of cellular respiration. So where would you find glucose? If I'm looking for glucose in the world, where am I going to find it?
Beans. Fine.
In your blood. Glucose is blood sugar, right? All right. Other sugars you eat, your body will convert. All right. Because you don't want to have like fructose and stuff floating around in your blood. That's not how it works. So yes, the number of carbons usually ranges somewhere from 3 to 7. And most monosaccharide names end with a suffix. What do you suppose, James? Ose, yes, OSE, glucose, maltose, dextrose, galactose, lactose. They all end in OSE. Where do you find lactose?
Milk.
Milk. It's milk, sugar, correct?
Yeah.
Right. Remember I said your body will convert? If your body doesn't do a real good job of converting that lactose into glucose, then you are
Lactose intolerant.
Now, who did biology and remembers this whole homeostasis concept that you have a membrane here, and you have a concentration here and a concentration here?
Oh,
Yeah, you want the concentration equal on both sides. What happens if you got a lot of lactose on one side and not much on the other? Sugars, too much sugar over here that's not converting, not enough sugar over here. What's your body gonna do?
Kind of like this.
Pull water into that intestine to dilute that sugar concentration, and then what's gonna happen to you? Oh yeah, that's my male bluebird up there. If you have extra water, yes, you will be in a bad way. You will be hoping there is a toilet nearby. That is, So if the sugar has an aldehyde group, we're going to call it an aldose. If the sugar has a ketone group, we're going to call it a ketose. And this is just how it works. Depending on the number of carbons in a sugar, they may also be known as trioses, pentoses, or hexoses, depending on whether they have 3, 5, or 6 carbons, etc. Right? So what do you suppose a disaccharide is? Caitlin? 2. Very good. So in this case, we are going to have two. So you have two monosaccharides that undergo a dehydration reaction. What do you suppose a dehydration would mean? Water went away. So you've taken out a water molecule. So now you have two monosaccharides. They combine and you have now a disaccharide. Very good. This is why organic is so fun, right? So during this process, the hydroxyl group of one monosaccharide combines with the hydrogen of another monosaccharide, releases a molecule of water, poof, there it goes, forms a covalent bond, and now you have a disaccharide. Covalent bond formed between the carbohydrate molecule and another molecule, in this case between two monosaccharides. Anybody know what we call that kind of bond? This is called a glycosidic bond. And glycosidic bonds, sometimes they call them glycosidic linkages, and they can be alpha or beta type. Oh, organic chemistry is so fun. Alpha bond is formed when your hydroxyl group on the carbon one is on the carbon one of the first glucose below the ring plane, and then your beta is when it is above the ring plane. Here's your ring plane. Some are below, see, some are above. And if they're above, you've got a beta. If it's below, you have an alpha. And remember when I said, like last week, when you start talking about, you get into these ring structures and whatever in organic chemistry, this is an example of where they are. Here they are. We went from nice, straight, our little monosaccharides. Remember, they were these nice little straight chains. And then when you start taking that water out, you get nice little rings. All right, so then polysaccharide would be what? Poly is? Multiple or many, right? So we go from mono to di to poly, and there's actually a little step in between, which I'll show you in a second in a flow chart. And these can be either one of two things, one at the top and one there. What's the difference between the two structures there?
One, like a little thing off of it.
Yeah, Jordan?
One is a long strip, the other one is.
Yeah, how would you describe this? Does it look like anything you've seen? Any kind of structure in life that you might go, oh, that looks like a... Ah, you got it, spot on. So they are either branched or unbranched. And that one would be unbranched, and this guy would clearly be branched. Looks just like a tree branch, right? Very good. So then you've got, they can contain different types of monosaccharides. So here are your monosaccharides chunking together. They can be all different types in there. They go in different orders. There's all kinds of structures. They get very complex. The molecular weight can be 100,000 Daltons or more. So these are big, big, big molecules. And that depends on the number of monomers joined. What's a monomer?
Singular polymer.
One unit, right? So we had polymers last week. We had monomer, not last week, before last. We had monomers and polymers. Monomers are your single units. Polymers are your chain of single units. So depending on the number of monomers joined, you can have very, very heavy, large organic molecules. So starch, glycogen, cellulose, and chitin are primary examples of polysaccharides. Okay, so let's look at cellulose. What is cellulose? Does anyone know where you find cellulose? James? Plant cells. Cellulose is found in the cell wall of plant cells. Okay, cellulose, when in your diet, we call it what? Anybody know?
Vegetable?
We call it fiber in your diet because we cannot digest cellulose. Okay, what little organism, little tiny white six-legged organism eats wood and can destroy your house? Termites. Okay, so you would assume then that although we can't digest cellulose, that a termite can, right? Because it eats the wood. It cannot. What? How do they eat the wood then? What happens?
They vomit.
Kind of, yeah, you know?
Bacteria in their stomachs that digest the wood.
Yes. Yes, termites have a microorganism in their gut that digests the cellulose. Even the termites that eat nothing but wood can't digest cell walls. So that's cellulose for you. Chitin. Anybody know what chitin is?
No.
You find chitin in two, that's keratin. You're close. You find chitin in two very diverse places. Do you know?
The shells of bugs.
Shells of bugs is one. Do you know where the other is? Yeah, fungus. Okay, so the cell walls in fungus is composed of chitin. And then you can also find chitin in the exoskeletons of arthropods. Two very diverse places where you can find chitin. All right, and those are all examples of polysaccharides. So Here are some monosaccharides. 3 examples of monosaccharides: glucose, galactose, fructose. Where do you find fructose? In fruit. Yeah, in fruit. There you go. All right, and then disaccharides. You can have lactose and sucrose. Lactose will break down into glucose and galactose. Sucrose will break down into glucose and fructose. What are you using in your body? Glucose. So if you drink milk and you break it down properly, you will have glucose. If you eat cane sugar and you break it down properly, you will eat glucose, right? Which is what you need. That's what your body will do. Now you've also got right here the other two more disaccharides: maltose, trehalose. Did anybody know where you find maltose? Malt. Think about it. Malt. Where does malt come from? Do you know? Oh, did it die? Oh, I love it when it does that. Twice today.
Oh my god, the freaking ring lady is gonna come out.
Yeah. There you go. Maltose you can find in grain, for example. It's the same sugar that gets fermented when you're making beer, because you use a mash and it's malt. There you go. And that will also break down into glucose. Now, then we have these. We talked about polysaccharides. We talked about mono and di, which are considered simple. And then we have complex. And we just talked about poly, but really you can kind of break that down further into oligosaccharides and polysaccharides. The oligosaccharides have 3 to 7 sugars, and then the polysaccharides have 10 or more. So some examples of oligosaccharides would be like raffinose, stachyose, verbicose, and they will all break down into these 3 different types of sugars, obviously glucose being one. So if you eat one of these, again, you can use it. And then polysaccharides, some good examples: starch, glycogen, dietary fiber, cellulose. Look at this. Does it break down? Do we break it down?
No.
Yep, it's not breaking down, right? So that's showing you there that you can't digest it. And here you've got starch, and that will break down into glucose. So again, if you eat nothing but pasta and bread and potatoes and stuff like that all day long, and then do no exercise of any kind, all that starch is going to break down into glucose. And then if you have all this extra glucose in your body, you may get a spike in your blood sugar for sure. But if you don't use that up, your body is going to convert it to fat and store it. Why does your body do that? What the heck for? Is it trying to be fat and unhealthy? What?
In case food gets cut off, you still need energy.
Yes. Does your body know that you're not living, 100,000, 400,000 years ago? Does your body know that? Does your body have any idea that you have like unlimited access to high fat, high carb food, just like right in your pantry, go to the grocery store? No, your body is evolved to deal with periods of scarcity and abundance. So if you have abundance, you pack on the fat because the scarcity might be coming and you're going to need something to eat, and you will basically eat your own body fat, right? What happens if you run out of body fat to digest and eat and fuel yourself with? James? Your muscles, and then eventually your bones will go and you will be in bad shape and you will starve to death, right? Right. All right, so carbohydrates undergo a process called condensation. We talked last week about condensation is when you do what? You add, what is it? Water again, right? So simple sugars can be combined to form larger sugar molecules called disaccharides or even polysaccharides. The reaction in which the simple sugars combine to form larger ones is condensation. And it's called condensation because a water molecule is generated in the process. So if you're making water in the process, it's condensation. The opposite, you're taking the water out, would be hydrolysis, right? So here's hydrolysis. So it's the opposite of, I just said, condensation, in which a polysaccharide or disaccharide is broken down into their constituent monomeric sugars known as hydrolysis. It's called hydrolysis because what's needed? What is needed to break the bond? Water molecule is needed to break the bond. And then your reaction mechanism for condensation reaction is the exact reverse mechanism for the hydrolysis reaction. Oh, here's our buddy, back with his long hair and unbuttoned shirt. So let's see what he has to say first about simple monosaccharides, and then what he has to say about polysaccharides, and if this will do its thing.
Challenges.
You have support from fellow students, faculty, administration, and they.
Hey, it's Professor Dave. Let's talk about carbohydrates.
He knows a lot about the science of Professor Dave explains.
We've all heard of carbohydrates and sugars, especially if we are loading up with energy for the big game or if we're on a diet. But many people don't know that these words refer to the same class of molecules. Carbohydrates got their name because they are literally hydrates of carbon, molecules with several carbon atoms that each bear a hydrogen and a hydroxyl group. When they are small, they are also known as sugars, and their names end in "-ose", like glucose or sucrose, which is the sugar that we commonly refer to as simply sugar. Let's learn about monosaccharides first. These are the monomeric units that polymerize to form polysaccharides. We can name these according to the number of carbon atoms they have, which will be between 3 and 6. So a 3-carbon monosaccharide would be a triose. If it has 4 carbon atoms, it's a tetrose. 5 carbons would be a pentose, and 6 would be a hexose. In addition, all carbohydrates will have either an aldehyde or a ketone functional group in the molecule. So we would refer to those as an aldose or a ketose, respectively.
Why do we have commercials in the middle, Professor Dave? Get it together.
Combining these conventions, we could refer to this monosaccharide as an aldohexose and this one as a ketopentose. Each of these carbons, the ones that bear both a hydrogen and a hydroxyl, will be a chiral center. And the convention for drawing linear monosaccharides is to use Fisher projections. When we look at these, it is important to understand that each vertex is a stereogenic carbon, and we show the hydrogens and hydroxyls on either side. With Fisher projections, horizontal lines are implied to be wedge bonds, and the vertical lines are implied to be dash bonds. To remember this, just imagine a bow tie on each carbon, like it's going to the chemistry prom. Fisher projections are just a different way of visualizing a molecule, which we can see if we draw this molecule in line notation and view it from the side. The Fisher projection is what we would see if we were in the plane of the screen looking directly at the chiral center. However we choose to view it, it's important to realize that Fisher projections do not imply a flat molecule with 90-degree bond angles. These carbons are still tetrahedral. We just save time by drawing sugars this way. When we draw linear monosaccharides, we always put the aldehyde or ketone at the top and draw the rest of the molecule downwards. And we report the stereochemistry of the molecule by looking at the chiral center at the bottom, furthest away from the carbonyl. If on this carbon, the hydroxyl points right, it's a D sugar. If it points left, it's an L sugar. So we would call this D-glucose, and this would be L-glucose. This terminology is a bit more outdated than the R and S we use to assign absolute configuration, but the convention has stuck around, and it remains the way that we differentiate between enantiomers of sugar molecules. We got this from glyceraldehyde, the simplest sugar, and an aldotriose. This has only one chiral center, and we developed D and L terminology according to the 2 enantiomers of this molecule. For some reason, nature has selected to work with D sugars. So unless otherwise stated, we can assume that we are talking about D sugars. Let's also note that since a molecule with N chiral centers has 2 to the N stereoisomers, there are 2 aldotrioses, the 2 glyceraldehydes, since there's only one chiral center on the molecule. There are 4 aldotetroses, these 2 and their L enantiomers. There are 8 aldopentoses, these 4 and their L enantiomers, because of the 3 stereocenters, and a total of 16 aldohexoses, these 8 and their L enantiomers. These differ only in the stereochemistry of these chiral centers. Lastly, with Fisher projections, let's be sure to understand that swapping the position of two groups on a chiral center results in the inversion of that stereocenter and a totally different molecule. And while 90-degree rotations are forbidden because they invert stereochemistry, 180-degree rotations are allowed. Monosaccharides exist in an equilibrium between a linear and a cyclic form, with the cyclic form being highly preferred. They cyclize by an intramolecular hemiacetal formation, a mechanism we learned in organic chemistry. We know that when hemiacetals form, it's because an alcohol attacks an aldehyde or ketone. In this case, it's an intramolecular cyclization because the hydroxyl group and the carbonyl are on the same compound. Now, let's orient this linear molecule in a way that we can see the cyclization take place. We know that carbonyl carbons are sp2 hybridized and therefore exhibit planar geometry. So when the hydroxyl attacks the carbonyl, it can do so from either side, thus generating two different stereoisomers, which are called anomers. It can either attack from this side, pushing the new hydroxyl down, resulting in the alpha anomer, or it can attack from this side, pushing the new hydroxyl up, resulting in the beta anomer. That makes the resulting hemiacetal carbon the anomeric carbon, because we can either get the alpha anomer or the beta anomer, depending on which side the hydroxyl attacks from.
Leon doesn't deserve the human-grade protein, real vegetables, and healthy whole grains.
When we draw cyclic monosaccharides, we sometimes use Haworth projections. With these, we look at the ring from the edge, meaning this part of the ring is closer to us, and this part is further away from us. And we show the functional groups projecting straight up and straight down. This does not accurately display the true geometry of the molecule, because we know six-membered rings like these prefer to be in a chair conformation. But Haworth projections have other practical uses. When we draw these, the convention is to place the anomeric carbon on the right and the CH2OH on the other side of the ring pointing up. If the new hydroxyl group that was generated during hemiacetal formation points down and is trans to this group, we have the alpha anomer. And if it is pointing up, cis to this group, we have the beta anomer. If a cyclic monosaccharide has a six-membered ring, we will call it a pyranose. But sometimes the hydroxyl on carbon 4 can do the attacking, resulting in a five-membered ring, which we will call a furanose. Rings smaller than this are unlikely to form due to ring strength. We should also note that monosaccharides don't always remain in the alpha or beta form. We can have an equilibrium between them, since the hemiacetal formation is completely reversible. This alpha glucose might go back to the linear form and then cyclize again to form the beta anomer. In fact, for glucose, the beta anomer is preferred because the hydroxyl on the anomeric carbon will be in the equatorial position versus axial in the alpha anomer. For this reason, a sample of glucose that has more of the alpha form than the beta will undergo mutarotation, which is a shift towards equilibrium values for the two anomers, which in the case of glucose is about 2-to-1 in favor of the beta anomer. A sugar will not always prefer the beta anomer. In some sugars, like mannose, the alpha anomer is preferred due to reasons of hyperconjugation that we call the anomeric effect. So we now know a bit about monosaccharides, their linear form, and the way they cyclize. And it is the cyclic form that is able to polymerize to form long polysaccharide chains. Let's learn about those next. Thanks for watching, guys. Subscribe to my channel for more.
Aren't y'all excited now for organic chemistry when you get to college?
Professor Dave explains.
Want to do more of that, right?
No idea what anything he was saying. He was like half speaking.
It's a lot. So I'm showing you these because I want you to get an idea of the scope. Oops, start over. So that's the part 2 of the same topic. I want you to understand that the scope is much broader than what we're doing.
Simple sugars like monosaccharides, but they also include polysaccharides, which are long polymers of these simple sugars. So we need to understand the way they polymerize as well as certain characteristics of the resulting polymers. First, let's return to our Hayworth projection for beta glucose. In the cyclic form, we can see there is a hemiacetal group. And if we remember the mechanism by which a hemiacetal will become an acetal, that is essentially what will happen here. We know that if this hydroxyl is protonated, it could leave, and then this carbon could be attacked by an alcohol, forming what we call a glycosidic bond, as well as an acetal functional group in the process. But if the alcohol that attacks is one of the hydroxyl groups on another monosaccharide, we will get a disaccharide. This is still an acetal functional group, but it links two monosaccharides together via a glycosidic bond. Here we have a beta glucose linked with another beta glucose, which makes cellobiose. Other common disaccharides are lactose, which is beta galactose and alpha glucose, and sucrose, or table sugar, which is alpha glucose and beta fructose. We could continue to polymerize further, making an oligosaccharide, which will have 3 to 10 saccharide units, or a polysaccharide. Polysaccharides can have thousands of monomeric units, and nature uses these quite frequently. For example, cellulose, which is abundant in plants, consists entirely of beta glucose units connected via 1,4 glycosidic bonds. This means that carbon 1, the anomeric carbon of one sugar, is connected to the hydroxyl on carbon 4 of another sugar, and it will extend in beta fashion from the anomeric carbon. This pattern can extend indefinitely, with beta glucose monomers connected in this way. Starch, which is abundant in potatoes and rice, is another polysaccharide made from glucose, and it only differs from cellulose in that all the glycosidic linkages are alpha instead of beta. This one difference in stereochemistry gives the molecule different properties. In addition, starch is comprised of amylose, starch molecules that are linear, and amylopectin, which is the same as amylose, except it has branching every 20 to 25 glucose units. The branching will occur between carbon 6 of one glucose and carbon 1 of another, and another chain initiates from there. Similar to amylopectin is glycogen, which also has alpha 1,4 linkages between glucose molecules, but glycogen has even more branching, occurring every 10 to 12 glucose units. Glycogen is an important way that we humans store energy inside our cells, and enzymes will break down some of this glycogen into individual glucose molecules in times of strenuous activity or in between meals, while other enzymes can add glucose units back to the chain to store them for later. So we now have a clearer picture of what carbohydrates are, from simple sugars like monosaccharides and disaccharides to huge polysaccharides with thousands of repeating units. These will come back later when we learn about cellular respiration. But for now, let's move on to another type of biomolecule, lipids. Thanks for watching, guys. Subscribe to my channel for more tutorials.
Yay,
And
Debbie.
as always, Professor Dave explains,
I don't know a little bit more.
So you know a little bit more. And he said we were moving on to lipids, so here are lipids. Anybody want to define a lipid for me? What you got, Caitlin?
Type of biochemical substance not dissolved in water.
There you go. So lipids are a class of organic compounds that are fatty acids or their derivatives. Their characteristics are that they are non-polar, which means they are insoluble in water. Why are they insoluble in water?
Because they don't solve.
Because water is
Polar
polar and like dissolves
in light.
like dissolves like, and if like dissolves like, then they are, if they are non-polar, they cannot be dissolved in water. Fats, oils, can they be dissolved in water? No, they cannot.
An emulsifier.
There you go. Yes, you would need an emulsifier to break it down or get it, clean it off, whatever. Yes. And they include many natural substances like oils, waxes, and steroids. Steroids meaning all kinds, the kind your body produces, the kind we produce in a lab. What do you use steroids for? What do you, James? Pain. It can be, inflammation. Yeah, what else?
Hitting home runs.
Hitting home runs, okay? So there are different types of steroids. There's corticosteroids that deal with like inflammation and whatever. There are anabolic steroids. Anabolic steroids are what Liam is referring to with hitting home runs, right? If you take anabolic, like there's been all kinds of, you hear about doping, right? With sports. That's what they're talking about. Taking a lot of the time, they're talking about performance enhancing drugs. Some of those are anabolic steroids. Yes, they can make you faster. They can make you stronger. They also can cause all kinds of other health problems. And has anybody heard the term associated with the type of temperament people on these?
Hot-headed.
Huh? Roid rage. Yeah, what's roid rage, Drew?
You take, those usually test for testosterone or something like that.
Yep.
Or try. Anyway, yeah, and you just kind of go crazy.
Turn into an aggressive jerk. Yes, yeah, absolutely you can. Now, steroids in general can do that to you. If you've ever, so here's an interesting one. If ever had laryngitis, it's often caused by a virus. The same virus in babies and small children doesn't cause laryngitis. It causes croup. You ever heard a baby with a croupy cough? It sounds like they're barking. You can take them out into the nice cold air if it's cold and hope that sometimes helps. But usually they give you something called Decadrone, which is a steroid. And you can turn into an absolute monster of a toddler on Decadrone. Like somebody in this room did that when they were little. it was monstrous. Yeah, they can make a baby really mean too. So it's not just like, oh yeah, you had croup twice, and after the first time I was like, oh God, here it comes again, because yeah, they give you Decadrone, yeah. Yeah, because it makes you better. I mean, because the problem with croup is croup can get so bad in babies that they cough so hard they just throw up, and it's really terrible. Like it's really terrible. You don't want it. Croup's terrible. And it can be fixed with the steroid because it's an anti-inflammatory. But your body makes steroids too. You know, it's not just the ones that you get from a doctor or inject or take or whatever. Your body makes steroids too. It's part of its normal communication. I'm covered in neurotransmitters. So these are like, you know, dopamine, serotonin, all those things. Yes, the messenger molecules. So here are some examples of lipids: triglycerides, phospholipids, steroids. Now, this one in particular is of particular importance. This is one you should really know. Phospholipids can form what's called a phospholipid bilayer. Anybody know where we find the phospholipid bilayer? Again, where? Cell membranes. Okay. Your phospholipid bilayer is made when you have your hydrophilic head and your hydrophobic tail. Hydrophilic. Break that down for me. What's it mean?
Water.
What's it mean? Water what? Hydrophilic. What's the philic? Loving, yeah. Water loving, water liking is hydrophilic. So then what is hydrophobic? We don't like the water, right? We don't like the water. So when you get a phospholipid bilayer like this, they orient themselves in such a way that you have your polar heads out and your non-polar tails in. This means that water, you've got it right there. You got a drawing of it. Water can be attracted to the outsides, but not in the middle. And this is what creates your cell membranes. And then you have these wonderful little channels and stuff in it and little molecules that like make little openings and little passageways for things to come in and out. But this is basically how your cell membranes are composed. And then we talked a little bit before about micelles, but a micelle looks like that. It's a sphere where all the tails point in and the heads point out. And you end up having something that can be used cosmetically. We talked about it as an example. Cosmetically, you can get micellar water. And it can take your makeup off, or it can just clean the oil off your face, because the oil will get trapped inside the little micelle because it's attracted to the tails, not the outside of the sphere. And it can just get stuck in there and washed away. All right, so another Professor Dave. We have a lot of Professor Dave today, but he's so good at this stuff.
Want to sell your car? You buy any car?
Hello,
Because
buy a
selling
car.
yourself means dealing with.
Okay.
Professor Dave here. Let's learn about lipids.
He knows a lot about the science stuff.
One's shorter than the last two. Okay. In the back. Pay
As we
attention.
continue our survey of biomolecules, we arrive at lipids. Lipids include things like fats, oils, and steroids. And the key characteristic that defines them is that they are largely non-polar, composed predominantly of long hydrocarbon chains or ring systems. And unlike the two types of polymers we've discussed, lipids are usually not big enough to be classified as macromolecules. Let's take a look at some different types of lipids. First, triacylglycerols, or TAGs. These are molecules with 3 ester groups, and examples include peanut oil, corn oil, butter, and lard. TAGs that are liquid at room temperature are called oils, and if they're solid, they're called fats. These molecules can differ in the type of acyl groups they possess, which is this portion of the molecule, which will always be a hydrocarbon chain of some length. If these ester groups are hydrolyzed, meaning a hydroxide attacks each carbonyl, kicking off this portion of the molecule, we get glycerol and 3 fatty acids. They're called fatty acids because they are carboxylic acids, but they also have long non-polar hydrocarbon tails, which can vary depending on the tag the fatty acid is derived from. Most of the time, this tail is unbranched and contains an even number of carbons. If it contains all carbon-carbon single bonds, this would be a saturated fatty acid because it contains the maximum number of hydrogen atoms possible. If there's a double bond, it's an unsaturated fatty acid. Sometimes there are 2 or 3 double bonds, which would make it a polyunsaturated fatty acid. In naturally occurring fats, the double bonds are almost always cis. When we hear about trans fats, these are the ones that seem to be harmful to the human body, as their linear shape gives them a higher melting point, so they are more likely to remain solid and more difficult to metabolize. These are associated with cardiovascular disease. In general, saturated fatty acids have higher melting points than unsaturated ones because the double bonds restrict rotation and therefore cause a kink in the chain, which interferes with crystal packing. Saturated fatty acids can pack neatly and maximize van der Waals attractions. That's why butter, which is fully saturated, is a solid at room temperature, whereas olive oil, which has a degree of unsaturation in one of its hydrocarbon chains, is less able to form an orderly solid lattice and is therefore a liquid at room temperature. An omega-3 fatty acid is one where the 3rd carbon from the end of the chain is participating in a double bond. When we talk about hydrogenated vegetable oils, these are derived by hydrogenating some of the double bonds in polyunsaturated fats. One problem with partial hydrogenation is that it can sometimes isomerize double bonds, turning cis into trans, resulting in trans fats, which, as we said, should be avoided. In general, fats like TAGs are used as energy storage. When these are metabolized in our bodies, they release twice as much energy as carbohydrates, since there are so many carbon-hydrogen bonds. Furthermore, polysaccharides like glycogen only provide energy for about a day, whereas the fats we store that make up around 20% of our body mass provide long-term energy storage, which would keep us alive for up to a month without any food intake if necessary. Still, there is much discussion about how much saturated fat and unsaturated fat should be in our diet, but we will have to examine that another day. Another interesting aspect of fatty acids is that when the carboxyl group is deprotonated to form the sodium salt, you get soap molecules, which have a polar head and a non-polar tail. These work by forming micelles in solution, where many soap molecules orient themselves with the negatively charged carboxylate groups all facing outwards to maximize ion dipole interactions with water molecules, while the hydrophobic hydrocarbon chains point inwards by exclusion, making van der Waals interactions with one another. Any non-polar dirt or grease, which is normally not water soluble, can get trapped inside and will then wash away with the micelle, which is water soluble. That's why washing your hands with just water alone won't do anything, but add some soap and the dirt gets transported away in little spheres of soap molecules. Let's discuss another type of lipid, the terpenes and the terpenoids. These are polymers made up of repeating isoprene units, which is this 5-carbon diene. Here we can see myrcene, a terpene consisting of 2 isoprene units. Farnesene, found in apples, has 3. The units can be linked to form rings, such as in limonene, which is found in lemons. These can get much larger, such as with beta carotene, comprised of 8 isoprene units, which is found in various plants and fruits. Terpenoids are similar to terpenes, but they contain oxygen atoms, such as with menthol, found in peppermint. Those are just a few types of lipids found in our bodies. Let's continue with lipids as we take a look at steroids. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email.
Okay. This one's the shortest of them all, but he covers everything so nicely and with great graphics that I can't do without him, so.
Thanks, Professor Dave. I'm going to tell you about steroids.
Professor Jane explains.
When people hear the word steroids, they typically think of anabolic steroids, which are synthetic derivatives of testosterone. But in actuality, steroids refer to a class of molecules that includes not just hormones, but also certain vitamins and cholesterol. Let's learn a bit about the structure and function of steroids. Steroids are all derivatives of this ring system, which is comprised of 4 rings. The A, B, and C rings are 6-membered rings, while the D ring is a 5-membered ring. There are also always methyl groups on these 2 carbons, and for ease of communication, we will always number this ring system the following way. This is carbon 1, and numbers 1 through 10 will wrap around rings A and B this way. Then carbon 11 jumps over to ring C, and we wrap around rings C and D. Lastly, numbering these 2 methyl groups like this. All the steroids we examine will be based on this structure. Now we know that 6-membered rings like to be in chair conformations. So let's see what that would actually look like. First, we should note that there are 2 common conformations for the A ring, either with a trans ring junction between A and B like this, or a cis junction, putting ring A like this. Also notice that the methyls are in the axial position, pointing upwards, and we will commonly refer to the substituents on the same side as those methyls as beta substituents, whereas ones on the other side, trans to the methyls, will be alpha substituents. The orientation of the A ring will depend on the hydrogen at carbon 5. If that hydrogen is alpha or on the dash bond, you get the trans AB junction. If the hydrogen is beta or on the wedge bond, you get the cis AB junction. Now, where else do steroids vary in structure? A common location for a substituent is carbon 17. Different alkyl groups at this location will generate different steroids, one of which is cholesterol. Cholesterol has 8 stereocenters, which means 256 different stereoisomers of this structure are possible, but only this specific one is cholesterol. This is an intermediate in the biosynthesis of all the steroids we need in our body. And although we often consume cholesterol, we don't need to because we also make it ourselves. So we will typically have more cholesterol than we need. And too much cholesterol in the diet leads to clogged arteries and heart problems. Let's look at another type of steroid, the sex hormones. These can be divided into 3 classes: the female hormones, or estrogens, the male hormones, or androgens, and pregnancy hormones, or progestins. Let's look at the female hormones first. These are estrone and estradiol, which differ only in the level of oxidation at carbon 17. Estradiol is secreted by the ovaries and kicks off the changes that occur during puberty, and also causes development of the mammary glands during pregnancy, whereas estrone is just a metabolized form of estradiol that is excreted. The male sex hormones, androsterone and testosterone, are incredibly similar to the female hormones, with the only differences occurring in the A ring. Similarly to the female hormones, testosterone does all the work, promoting the growth of body hair and facial hair, lowering of the voice, and other traits associated with puberty, whereas androsterone is just the metabolized version that is excreted into the urine. And progesterone is the most important pregnancy hormone, which prepares the uterine lining for implantation of a fertilized egg and suppresses further ovulation during pregnancy. Other hormones like cortisone and cortisol regulate many other biological activities, like metabolism and controlling inflammation. And that wraps up our survey of lipids. Thanks for watching, guys. Subscribe to my channel.
So had you thought about all of these different hormones and whatnot being lipids, being essentially fatty acids? We don't often think about it that way, but that's what they are, right? Which is why they're not water soluble, right? So it's always important to remember that. Ding, 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 ding. Sing me the song of my people, Jordan. All right, so now we have,
South Carolina.
oh, that's important.
Oh.
Put them on speaker. Hello. All right. So now we're going to talk about proteins. Now, part of the reason I showed you all those Professor Dave videos, and there's a method to my madness, aside from making sure that you understand the scope of the stuff we're talking about is way bigger than this little bit we're touching on here. Some of you may end up in an organic chemistry class in college. And if you're going, blah, 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 remember that Professor Dave has nice, clear videos that you can go back and look at and go, oh yeah, okay, he breaks it down so nicely, so neatly, so clearly, bless you, that may be a helpful tool for you. So we are barely touching the surface with this stuff. But if you're interested in like pharmaceuticals or getting, a degree in pharmacy or working in microbiology or working in pharmaceutical labs in particular, huge with this type of chemistry, but any sort of medical work, you'll have to do this kind of stuff. So proteins. Anybody want to define a protein for me? Caitlin. There you go. An organic compound that is made of amino acids. Okay, amino acids were today, your little codons were creating an amino acid, right? And then you put the amino acids together and you get a protein. And today that was represented as your sentence, right? All right. And that is actually how you do it. And they do it in groups of 3. That wasn't just for fun. That's how your DNA works. So these are amino acids arranged in a linear chain. And they're joined together between carboxyl atom of one amino acid and the amine nitrogen of another. But here's the thing about them. They are so long that they are almost always folded up. You can think about it like origami. If you take a piece of paper and you fold it into a crane, you recognize that it's a little origami crane, right? Like you can see the shape of the crane and your brain goes, oh, crane, right? Okay, that's kind of how your body works with proteins. The shape of the protein is very important, and the shape comes from how it folds itself up. So what kind of a bond is in a protein, Jordan? Peptide bonds, right? Okay, and these are what are in between your amino acids. So the sequence of amino acids in a protein is defined by a gene and encoded in the genetic code. How many amino acids do we have? 20, very good. So we have 20 amino acids that we produce. And it says, although the genetic code specifies 20 amino acids, the residues in a protein are often chemically altered in a post-translational modification. So either before or after the protein can function in a cell as part of control mechanisms. So you can end up with other amino acids after the protein's kind of done its job. But your body, your genetic code will code for 20 different amino acids. And then the order and organization of those within a chain will determine what protein you're building, and all those different proteins are necessary for your entire structure and a lot of the function of your body and all living things. So proteins can also work together to achieve a particular function, and they often associate to form stable complexes. Guys, stop. Do I need to move one of you? All right. Like other biological macromolecules means big molecule, right? Such as polysaccharides and nucleic acids, proteins are essential parts of all living organisms and participate in every process within cells. Now, you have 20 amino acids that you can produce from your genetic code, but there are some that you don't make, but you need. Where do we get them? From your food, right? This is why it's important to eat a diverse amount of food, because there are certain ingredients, certain things in those foods, certain molecules that your body needs to function that you cannot synthesize on your own. So many proteins are enzymes that catalyze biological reactions. An enzyme is a natural, an enzyme is a natural catalyst, right? And catalysts do what? Yep, by lowering what? Lowering the activation energy, right? Okay. So also other proteins have structural or mechanical functions, such as proteins in the cytoskeleton, which forms a system of scaffolding that maintains your cell shape. Your cells have a tiny little skeleton inside of them called a cytoskeleton. That's all protein. Proteins are also important in cell signaling, immune responses, adhesion, and the cell cycle. Your cells are programmed to divide and die. Divide, do their work, and die. There is an actual program in your cells that reads die now or whatever, and then your cells die. What happens if they don't?
Cancer.
That's where cancer comes from. Now, they just start dividing uncontrollably and they don't die. Chances are everybody in this room has had cancer today, but your immune system took care of it before it was a problem. Your immune system goes, oh, no, you're supposed to be dead. Kick it out, whatever, right? If your immune system misses it, or if it overwhelms your immune system, that's when you get cancer that then affects your body. And then the way our bodies work is you have these little cells that their coding is wrong, and now they're multiplying rapidly and they're not dying. And that usually that can be in your genetic code. There are some cancers that tend to run in families, right? But that also can be because you've had something called tetragenic experience, where you basically had something that impacted those cells, and that DNA and that coding gets corrupted in some way. And then that is producing the signaling to keep multiplying and not die. Those are things like UV light, anything we call carcinogenic, cancer causing. That's what it does, is it impacts the genetic code within your cells that says stop dividing and die. So that's how you get cancer from other things, right? Like skin cancer from the sun, or different lung cancer from cigarettes, because those chemicals have impacted the way your cells are supposed to function. So proteins are important, like we said, cell cycle, whatnot. And protein is also a necessary component of our diet, since animals cannot synthesize all the amino acids and must obtain essential amino acids from food, which is what we just said. Through the process of digestion, animals break down ingested protein into free amino acids that can be used for protein synthesis. Now, this is fascinating too. There are certain disorders where your body does not recognize proteins that you eat as a safe thing and a good thing. And there is a miscoding where your body recognizes it as an invader or a parasite. It's not reading it correctly. So then your immune system will attack that. And basically it makes it so that there are certain kinds of food that you cannot eat. And this is not like a regular allergy. This is different. There'll be foods that you can't eat, and there will be sometimes lots of them, not like one or two. We're talking like, thank you. We're talking like dozens and dozens of types of food where the proteins trigger your immune system. And in that case, the way they do it is, remember we said it's a long chain of amino acids. We need the amino acids because we're going to they're like building blocks. We're going to take them and reconfigure them and make them into what we want them to be. We're going to take them from the food, this big folded up thing. It's almost like a big stack of Legos or a Lego structure, and you're going to take it apart and you have all the individual Legos, and you need those Legos. You don't need the big thing anymore. So what we are able to do now is we're able to break down all these different proteins into just the amino acids. And then there's a formula that you can consume, and it tastes terrible. So most people that have to do it through a feeding tube because it's gross. But you can get all of your amino acids through a formula and avoid food entirely. Stop. And if your gut doesn't function well, you can also have some of that given through an IV. And that's called TPN, total parenteral nutrition. That's all through, you can be fed through an IV.
I had a friend who
of eating too.
Do you know why?
She
It was something with the.
Eosinophilic esophagitis. That's what Cole has. Yeah, yep. That's why I know a lot about it. Yep. His is not, he can manage with a topical corticosteroid that he has to swallow to keep inflammation in his esophagus down. Otherwise, he would be right there. And chances are I probably know that friend or their mom. So anyway, yep, those types of disorders in particular cause those problems. All right, so proteins are formed by condensation of amino acids. Again, condensation chemically means adding, what are we adding to it? We're adding water, right? Condensation is you're adding water. All right, so here are some examples of amino acids by side chains. So you got all these different amino acids, and remember, like, we start adding them onto these chains, and that's how we get all these different looking proteins, and then we fold them all up nice and neat. Here are some others. Woo, look how complicated. So see, these are a little differently denoted. Well, no, these are the same type of structures. Yeah, but remember, he showed you how you can draw them different ways. It kind of gives you an idea of what the 3D appearance is like as compared to some sort of linear, like these are very linear. All right, so the form and function of a protein depends on its three-dimensional shape. If you take a piece of paper and you fold it into a paper airplane, now you have a three-dimensional shape, you can throw it, and that is how it is going to function because of its form, right? It will fly if you've done it decently. If you take a regular piece of paper and just throw it, it's not going to do the same thing. If you take it in a ball and throw it, it's not going to do the same thing as a paper airplane would do. It's because the form, the function relates to the form, and that all has to do with how it's folded up. So, for example, you got this amino acid chain just looking like this, and it can fold itself up in different ways. It can make helixes, pleated sheets, these tertiary structures like this, these quaternary structures like this. They can get very, very, very complicated. Some of them are very large and they're folded up all kind of ways. So other examples of structures, primary, secondary, tertiary, and quaternary structures. This is complex protein here. This is just amino acids. You get helixes and polypeptide chains. And whatever shape they come in is going to impact how it functions. Here are some proteins in your body. So proteins can include your immune system, such as antibodies, which are there to fight invaders, right? They're going to fight primarily bacterial invaders and other things like that. Your complement immune system has 20 protein molecules that are activated when you have infections. So you have your immune system that's doing its job all day long. If something gets in, it gets past the goalie, it gets in, you got a problem. Now your complement immune system is going to kick in and do its job. You have proteins in your muscles. You have actin and myosin. Have anybody ever seen a ratchet? How a ratchet works? So it's got teeth and it goes along like a little ridged edge and it locks in each time. That's how actin and myosin work. Yeah, in your muscles, it's literally like a little ratchet. It moves along as your muscle cells contract. And as they relax, it just releases and lets them go. So it works the same way a mechanical ratchet works. Those are both proteins, actin and myosin. Notice a lot of these are going to end in IN. That's just how we name our proteins. Yeah.
There's a cool protein called ATP simple,
Uh-huh.
and it makes ATP, which you need for
Yep.
living.
Yep.
But it takes the phosphate group,
Mm-hmm.
attaches it by crushing them together.
Yep.
Because it's a motor that electrons spin down to power.
It's pretty fascinating. It's like a factory. Yep. Uh-huh. It's like a factory. Yeah. It's
There's a cool protein.
there's a cool protein. It is. It's literally like a whole factory within a protein. It's pretty wild. So then you have stuff like myoglobin that helps release oxygen into your muscles. So you've got, your hemoglobin is transporting it, and then you got myoglobin, which isn't, it's there to actually do the work of taking that oxygen and putting it to work in your muscles. Ferritin stores and releases oxygen. Ferritin, what can you tell me about ferritin based on the name? Got something to do with iron, right? You see that F-E-R-R in there? There you go again, right? All these, they come back to you all the time. Cytoskeleton, again, that's your structure within your cells. And then you've got keratin. That's what you mentioned earlier, PJ. Keratin is in your skin, your hair, and your nails. That's what keratin is. You can get keratin treatments. If you've got long hair, you can go in and they will infuse extra keratin into your hair shafts, and then blow dry it out. It looks all silky, and I don't know how much it costs because I'm not spending money on that. But yeah, you can get that done. I bought the at-home ones. That's easy. But yeah, you can get that done. But keratin's in your skin. It's in your nails. There's some people that lack keratin and then have disorders where, like, excuse me, they will scar very easily because their bodies don't produce it the same way that it should be done. Elastin. Anybody want to guess what elastin does based on the name? It says a little bit, provides flexibility. So where are you going to find elastin, do you think?
Muscles, so that the face can move.
Yeah, skin, muscles. What else? Lucas? Tendons. Yep. Tendons, skin, muscles, joints. Yeah. Vocal cords, all these places. Now, here's an interesting thing about elastin. We all have a certain amount of elastin. Some people have way more. There are disorders for that too. But during pregnancy, the body will produce lots of elastin. And you can actually get all of your joints more flexible during pregnancy, though you don't feel like you want to be flexing everywhere, because especially towards the end, when it starts producing lots of elastin, you can get real flexible. Why? Why do we want our joints more flexible during, especially towards the end of pregnancy? What do you think?
Push the baby.
Really?
Push a giant baby out of you.
Yeah, because your pelvic girdle needs to stretch and open to allow for, size of a watermelon. There's something the size of a watermelon out of something the size of a lemon. Yeah, that's the worst. But yeah, you have to have your pelvic girdle stretch open to allow for birth. So you get more elastin towards the end of your pregnancy. You can actually, your pelvis will actually stretch more, as it's apt to do. So these are all like super important.
Apparently, it's harder to birth a little person because, like, the size of their head is going to be the same size as
Yep.
when they're grown.
Depending on the type of achondroplasia you're dealing with, there are some types of achondroplasia or dwarfism where, yes, the little person's head will be larger at birth than your typical infant head. Now, infant heads and typically infant heads are going to like collapse to a degree, right? The bones are not connected. They're all separate and they're kind of free floating to a degree, and you can actually squish it. And babies born vaginally tend to have little cones on their heads for the first day or two, and it will slowly just mush back down, but they're born with little pointy heads, right? So yes, that's the point of something like elastin. And it's essential. Without it, we'd be in a bad way. But that's also why some people, when they, like, some ladies tend to get injuries at the end of their pregnancy, like sprained ankles and stuff. Whoop, you're already off balance, and then that happens. So then you have your signaling proteins, your cytokines that communicate with other cells. These are like your neurotransmitters, some of your steroids, those types of things, right? Your sex hormones, all those hormones, those are all falling into this group. Your proteins in your blood, hemoglobin transports your oxygen. We know that, right? Fibrinogen, I cannot speak, helps with clotting. And then albumin, which is within your blood, contains, it's a lot of the liquid portion of your blood is albumin. And then we have enzymes, digestive enzymes that help break down food. And then we talked about phospholipid bilayers in our cell membranes, right? There are channels in there. Proteins make certain channels. Literally, it's like a pass-through, like a train tunnel going from one side to the other where things can come in and out. Cell transport is fascinating. Some of it is passive, like it just floats through, like it's just driving on through. And then others require a certain amount of energy. There's a lot of electrical capacity involved. There are sodium and potassium channels where you have like an electrical difference on one side or the other side that pulls things through, pushes things out. It gets very, very involved. Enzymes, receptors, and then your 3 types of proteins: peripheral proteins, integral proteins, and lipid-bound proteins are right within your cell membranes. So all of that. All right, he's got a little bit more on that. We had a lot of Dave today.
Do it for life.
Gotta love Dave. Yeah.
Professor Dave here. Let's talk about amino acids.
He knows a lot about the science stuff. Professor Dave explains.
Your body is full of large molecules called biomolecules. And the first thing we have to do to understand biochemistry is to learn about the different kinds of biomolecules. There are a few different classes like proteins, carbohydrates, lipids, and nucleic acids. And most of them are polymers that are comprised of repeating units called monomers. Mono means one, poly means many. So a polymer is formed when many monomers link together. Each polymer has its own type of monomer. So we need to know about these different kinds of monomeric units and the ways they combine to form the large molecules that do all the complex things in your body. The first type of monomer we will learn about is the amino acid. Amino acids look like this. They all have an amino group on one end and a carboxyl group on the other end. The carbon in between those functional groups, which we call the alpha carbon, will bear a side chain, sometimes referred to as an R group. This is a group that varies depending on which amino acid we are looking at. If the R group is just a hydrogen atom, we call this amino acid glycine. If it's a methyl group, we call this alanine. There are about 20 of them, and they have a wide variety of R groups that can be put into different categories. Some of them will be hydrophobic, like leucine. These are the ones with R groups that are alkyl substituents. Some of them have R groups that are aromatic, like phenylalanine. Some have R groups that are basic, like lysine, because of the lone pair of electrons on the nitrogen atom. Some have R groups that are acidic, like aspartic acid, because of the carboxyl group. Some have R groups that can act as nucleophiles, like serine, because of the hydroxyl group. Every amino acid has its own unique structure and reactivity, and it's the variation in these R groups that determines the characteristics of the molecule that forms when a bunch of these amino acids join together. Some of these amino acids humans can't make on their own, so we have to eat them in our diet. They are called essential amino acids. Others we are able to make inside our bodies, so those are called non-essential amino acids, meaning it's not essential that we eat them. So amino acids are monomers, and monomers are the units that join together to form a polymer. How exactly then do amino acids polymerize? Before we learn about that, let's first understand that inside the body, instead of the one structure we've been looking at, there are actually equilibria between different forms of the amino acid. The amino group can be protonated, since it is slightly basic, and the carboxyl group can be deprotonated, since it is slightly acidic. And there are equilibria between the cationic form, the zwitterionic form,
That's a fun
and the anionic.
Here we go.
Cations and anions, they're positively charged with negatively charged station. And a zwitterion is a molecule that has both a positive and negative charge. The form that an amino acid will take depends on the pH of its environment. A more acidic solution will favor the cationic form, since basic groups will pick up protons from the hydronium in solution. And a more basic solution will favor the anionic form, since acidic groups will readily deprotonate in the presence of hydroxide. Inside the body, the pH is regulated very precisely, and in most areas, it's fairly close to neutral pH, so the zwitterionic form is typically dominant. The side chains can also have different states of protonation or deprotonation depending on the pH, such as lysine, where the R group can have NH2 or NH3+. For now, let's just look at something simple like alanine. At physiological pH, it will take this form. What sort of chemistry can this do? It might not be obvious just looking at it, but with the help of other molecules in the body, these can polymerize to form proteins. So let's move ahead and learn all about proteins. Thanks for watching, guys. Subscribe to my channel.
And I think this is our last one here. He's going to show you how these all fold together. And I'm actually, I think we're good. Yeah, we got it.
Hey guys, it's Professor Dave. I want to tell you about proteins.
He knows all about the science of Professor Dave explains.
So we know about amino acids, and these are the monomers that will form proteins, which are also known as polypeptides. Proteins are polymers of amino acids, and they are the most diverse type of biomolecule in your body. Different kinds of proteins include enzymes that catalyze chemical reactions, receptors that control signaling in your body, hemoglobin, which carries oxygen throughout the bloodstream, muscle and organ tissue, which give your body structure and mobility, and so many other things. So how do amino acids polymerize? This happens when amino acids form peptide bonds with one another, such as the peptide bond between these two glycine units. Peptide bond formation is an example of a dehydration reaction because the two hydrogens and the oxygen marked in blue are lost, and two hydrogens plus one oxygen equals a water molecule. So as a water molecule is lost, these two amino acids come together to form a peptide bond, which results in an amide. An amide is a functional group with a nitrogen atom next to a carbonyl, and this is the functional group that will connect each amino acid during polymerization. If two amino acids combine, we get a dipeptide. If between 3 and 10 come together, we would call that an oligopeptide, since oligo means just a few. And if more
Just a
than
few.
10 come together, we will call that a polypeptide, since poly means many, and proteins are large polypeptides of around 300 to 1,000 amino acids that are folded in such a way that they have some biological activity. When we look at any peptide, we must notice that there is an N terminus, meaning the side of the chain that ends with the amino group, and a C terminus, the side that ends with the carboxyl group. By convention, we typically write proteins with the N terminus on the left and the C terminus on the right. Each monomeric unit in the polypeptide is called a residue. So on this structure, we should be able to differentiate between each individual residue and locate the peptide bonds that connect them. Proteins are very large compared to simple molecules. They contain hundreds of amino acid residues, and they have very specific shapes from which their function is derived. So let's learn about protein structure. Protein structure follows a specific hierarchy. So let's start first with primary protein structure. The primary structure of a protein is simply the sequence of amino acids with no attention paid to any aspect of three-dimensional shape. We can abbreviate each amino acid residue with either a 3-letter code or a 1-letter code, depending on how much you feel like writing. And here are both sets of abbreviations for your reference. The shape the protein will take depends on the primary structure because it is the identity of all the side chains and the sequence they are found in that determines how a protein will fold up. To see this in action, let's look at secondary protein structure. Secondary protein structure describes localized conformations of the polypeptide backbone, meaning the folding pattern that a protein will exhibit over a few dozen amino acid residues. There are a few different motifs that a protein can utilize, so let's see what those are. First, let's understand that the backbone itself is essentially planar. The peptide bond has some pi bond character due to resonance, since there is a resonance structure where the lone pair on the nitrogen forms a pi bond, pushing the pi bond in the carbonyl up to the oxygen atom. We know that rotation is restricted around pi bonds, so even though it's not a formal pi bond between the carbon and the nitrogen, the backbone is fairly rigid, while the sigma bonds to the R groups can freely rotate. So it is mainly the side chains on each residue that have a flexible conformation.
Right.
We also know that
Everybody's
molecules
going.
with dipoles or formal charges will attempt to store energy by making electrostatic interactions, and amino acids have such features. So if this backbone can fold in such a way so as to let each residue interact with other residues, it will do so in order to adopt the lowest energy conformation. One way it can do this is by forming something called a beta-pleated sheet. The backbone will extend one way and then turn back to line up alongside the first part of the chain, so that NH bonds from one section can form dipole-dipole interactions with the carbonyls of an adjacent section. This stores energy, so it is an example of a favorable conformation and one type of secondary protein structure. Another type of structural motif is called the alpha helix. This is when the backbone forms a spiral shape with about 3 or 4 amino acids per turn, and all the R groups pointing out. Here, each amide group will interact with the amide group 3 residues above and the one 3 residues below. So beta pleated sheets and alpha helices are the most common types of secondary structure, though there are all kinds of other coils and loops that are a bit more difficult to describe. The key thing to understand is that at this level, the polypeptide backbone begins to form shapes entirely dependent on how it can best store energy in dipole-dipole interactions by adopting the lowest energy conformation. And these structures contain so many individual atoms that we begin to depict them as colored strips rather than with conventional molecular line notation.
So I'm gonna pause him because he'll go on forever about this, but you get the point, right? That your side chains and all of those different little functional groups that get added in are what cause the shape to be what the shape is. And that the shape then determines the function. The last thing I have is actually a very fun summary. But before we go over that, before we go over the summary, so they touch on DNA, which is what we did today in lab. And at one point in this video, they say that DNA, your complete genetic code is in most of your cells. But we have some exceptions to that. And I'm wondering if anyone knows what the exceptions are. Where will you not find your complete genetic code within your body, James? Gametes, which are your sex cells, and there's another one.
Feces.
Those are not cells in your body, but good guess. All right. Your red blood cells do not contain your full, there you go. Do not contain your full genetic code. They don't. And then obviously your sex cells, your gametes, eggs or sperm, contain half your genetic code at a very random selection of which half, right? So yes, so next week in lab, what we'll be collecting are the squamous epithelial cells that are inside of your cheek. It's the same thing that they use for buccal swab. If you've ever seen like law enforcement or whatever, they do the DNA test, they do buccal swab. And if you've ever done like a commercial DNA test, like a 23andMe or a Ancestry.com, you spit in the little vial and it's picking up enough of those cells. We're good enough now that you can just take spit and pull DNA out of it that can be used. Now, the DNA that we're going to pull out isn't going to be of really any use to us for doing much of anything except pulling out this thing that looks like this clump of white goo and going, ah! And you have it. You're like, oh, it's DNA coming out of your cells. And it's really, it's actually a very fun lab. Although you will have to swish salt water around in your mouths and you may not like it. Some people get really grossed out by it, but you like salt. So this is our summary. It's Amoeba Sisters. They put out a really good version of this years ago, and then they updated it in 2023. So if you go back to watch it, use this link or be sure that you're checking for the updated version because it's a much more thorough.
Match of Robin of Gold, the record they have.
Yeah, okay.
No one does food like Puerto Rico. There's a chef tasting menu for a local favorite spot.
I want you to think for a moment about your favorite food. What is it? We all have different food preferences, but food is a source of large molecules that are needed for life, called biomolecules, also known as macromolecules, carbohydrates, lipids, proteins, and nucleic acids. In different types of food, you might find higher amounts of these biomolecules. For example, peanut butter can be high in both proteins and lipids. And while we'll mention examples of foods that contain different biomolecules in this video, this is not a video on nutrition. This is a video on the classes of biomolecules and their importance to the structure and function of cells, and therefore also to the entire organism, because organisms consist of these cells. Before we get into details about the 4 biomolecules, we need to talk about one very important vocabulary word, the word monomer. Monomer is a building block. If I had some large substance, the parts that make up that substance are called monomers. With each biomolecule class, we will mention its monomer if it applies. We'll start with the biomolecule class of carbohydrates. Generally, food sources such as bread, pasta, fruits, and vegetables tend to be high in carbohydrates. The monomer of a carbohydrate, remember, and this is the building block, is the monosaccharide. One example of a monosaccharide is the sugar glucose. Glucose is a pretty big deal considering it's used in cellular respiration to make ATP, an energy currency. If two monosaccharides, such as glucose, are combined, you get a disaccharide. For example, put these two glucose sugars together and you get the disaccharide maltose. By the way, a lot of sugars have that OSE ending. Glucose, maltose, lactose, sucrose, fructose, I could go on. The ending OSE be a carbohydrate glue. If you join a lot of monosaccharides together, that can combine to make a polysaccharide, a big carbohydrate. So how are carbohydrates important to an organism and the structure and function of its cells? Well, plants have cell walls of carbohydrates, specifically a large one known as cellulose. Fungi have cell walls of carbohydrates too, specifically one known as chitin. Fun fact that carbohydrate chitin is also what makes up the exoskeleton of insects. We mentioned glucose is used to make ATP. That makes carbohydrates a fast source of energy for cells. So that's a big function for carbs, major energy source that cells can access. That energy can be stored in a polysaccharide form. Remember, polysaccharide, big carbohydrate, such as starch for plants or glycogen for animals. Next up, lipids. Lipids include fats and oils. Examples of food sources could include butter or olive oil. This is a seriously diverse group, meaning there are a lot of types of lipids. There are triglycerides, there are phospholipids, there are steroids. These are just some examples. Most, but not all, lipids have building blocks of glycerol and fatty acids. One thing though that lipids generally share, generally they're hydrophobic, or at least contain a significant hydrophobic component. That means lipids, or at least a major component of them, don't like water. Lipids generally won't dissolve in water. And that's interesting, is generally the other biomolecules will. So how are lipids important to an organism in the structure and function of its cells? Remember how we said all cells, plant cells, animal cells, all cells have membranes? Well, thank you phospholipids for that phospholipid bilayer, because that's right, lipids make up cell membrane structure. Lipids have a major function of being a source of long-term energy storage. Remember how we said carbohydrates were a fast source of energy, but when those carbs are used up, lipids have a function as long-term energy storage that an organism can use. Lipids are also very important for different types of insulation. The insulation may involve helping a cell carry an electrical impulse. For example, this myelin sheath made of lipids that can be found on many neurons. Or the insulation may involve
The lack of that sheath is what causes multiple sclerosis.
For example, the blubber on this adult front seal is made of lipids, helping it conserve heat. Another cool function about lipids, many lipids act as hormones, which are chemical messengers for many different processes. Next up, proteins. Protein food sources include beans, meat, nuts, and eggs. The monomer of a protein is an amino acid. Usually proteins consist of many amino acids bonded together. There are different types of amino acids. So how are proteins important to an organism in the structure and function of its cells? Structure-wise, tissue like muscle tissue consists heavily of proteins. Proteins can make up all kinds of other structures, hair or collagen, for example. Proteins can also be found embedded in cell membranes as protein channels. And channels are important to that cell membrane structure with functions of letting certain substances pass through. Proteins can also be receptors, which are critical in cell signaling, so cells can coordinate actions together. Most enzymes are made of proteins. Remember, enzymes can build up or break down substances in all kinds of metabolic processes. Antibodies, which are made by immune cells in your body, are proteins, and they are involved in protecting your body. And some critical hormones, such as insulin, are proteins. And when we start talking about genes, genes are made of DNA, but many genes do code for proteins. And that brings us to our last one that includes DNA, nucleic acids. Nucleic acids include DNA and RNA, which we'll get to in more depth when we get to genetics. Nucleic acids have a monomer called a nucleotide. It's going to be an easy one for you to remember because nucleotide sounds like nucleic acid. By the way, you might wonder, are nucleic acids like DNA and RNA found in my food? And the answer would be yes. Whenever you eat something that came from something living, it actually could still have DNA inside it. For example, when you eat a strawberry, you're actually crunching all the cells that made up that strawberry, and in the nucleus of all those strawberry cells is DNA. Any type of life, like plants or animals or fungi or bacteria, they must contain nucleic acids like DNA to direct the cell's activity. How are nucleic acids important for your cells? Well, most of your cells contain all of your genetic information in the form of nucleic acids, DNA and RNA, and this is needed for the coding of your traits. Traits involved in structure and various functions. Okay, so we just did a very general tour of 4 biomolecules. Before we go, I just want to marvel at biomolecule structure because it's absolutely beautiful. So if I arrange them in the order we did, carbs, lipids, proteins, and nucleic acids, how might you remember the major and most common element in them? There's a popular mnemonic known as CHO, CHO, CHOM, CHOM, although it's CHOMP with an N. To help me remember the C for carbon, H for hydrogen, O for oxygen, N for nitrogen, and P for phosphorus. Does that mean you won't find other elements in the biomolecules? Of course not, but it's important to understand the arrangement of these elements and biomolecules because the structure of the arrangement greatly impacts their function. You can learn more in our further reading suggestions in the description. Well, that's it for the Amoeba Sisters.
Okay, so that's that. You got your coins up there. We will catch you next week. Good job today. Everybody did real well.
So funny thing happened.
Hmm.
I'm in the wrong address.
Oh no, where'd it go?
6465 with the foot place.
6465.
Oh, I'm not.
Had somebody else's address going, did we?
Yeah.
Oh well.
So, I'm just gonna cut my losses and not do anything. I'm not gonna confuse that that's what happened.
Where'd you 6465 where?
Like Rutherford Place.
Rutherford Place. Oh,
Yeah.
that's a whole, yeah, that's a
Yeah.
whole one over.